In this video, we're going to talk about another business application that is involved with binary decision variables, location optimization. So in location optimization problems that are usually formulated as pure binary integer programming problems, the objective is to find the best set of locations, the best set of location out of a list of um, alternative locations, right? In order to meet a certain objective function. And then objective function can be different. Sometimes you want to find the minimum number of locations that is enough to cover the whole region. And because of that, these type of problems are also called covering problems or set covering problems. So let us go through one specific example. Ohio Trust Company, which is considering expanding their operation into a 20 county region in northeastern Ohio. So there are 20 regions, and the decision that they have to make is where on this region they have to they want to actually open new principal places of business. So currently they don't have any principal place of business in any of these 20 counties. And then there is a law that says, according to the banking laws in Ohio, if a bank wants to if the bank wants to work in a certain county, they have to have a principal place of business or PPB either in that specific county or in one of its neighbor counties. So this is a very important condition that they have to maintain in order to be able to operate in a certain region. For a region to be able to be covered by Ohio Trust Company, they have to either have a PPB at that region, at that county, or in one of its adjacent counties. All right. So, this is important. They want to get that. So here we have the list of all the 20 counties. And we also have the list for each county, we know exactly what are the adjacent counties, what are the neighbor counties that if we have a PPB there, they can cover those counties as well. So for example, for county number 1, Ashtabula, itself is covered. If you have a PPB here, that's fine. But then if you have a PPB at 2 or 12 or 16, these are the county numbers, right? They can also cover county number 1 because these are considered to be neighbors of county 1. And let's say for county number 20, it's neighbor with counties number 11, 14, and 19. So if you have a PPB at either of these 4, either at 20, 11, 14, or 19, county 20 can be covered. County 20 can be under Ohio Trust Company's operation. All right. So in order to be able to operate in this county, you should have either a PPB at this county or at one of its neighbors, either at 11, 14, 19. Right. So if you get the logic, we need to make 20 questions. We need to make 20 decisions. Ohio Trust Company needs to make 20 decisions, whether or not to open a new PPB at county number 1, county number 2, all the way to county number 20. 20 binary type of decisions they have to make. And Their objective right now is that they want to understand what is the minimum number of PPBs in order to be able to do business throughout the region. I mean, they want to cover the whole region, but their objective is to find the minimum number of PPBs and their location, of course. Where should be their PPBs located in order to be able to cover the whole set, to cover the whole region, all right? So our decisions, all of our 20 decisions that we have to make, they have a binary nature, yes or no type of decision. So this is going to be a pure binary integer programming model. And the decisions like we defined, it's going to be binary, whether you open a PPB at county I or not. So this is going to be the decision. And in the next slide, I have the full formulation. So the objective function, we want to find the minimum number of PPBs that can cover the whole region. So minimum, and then we define decision variables. If we have a county at county, if we have a PPB at county number 1, county number 2, county number 20. If we add them together, it's going to give us the number of PPBs to be established, right? So because these can be, each one of these 20 decision variables can be either 0 or 1. 1 meaning we will open a PPB there. So if, let's say, all of them are equal to 1, when you add them together, you're going to get 20, meaning that you will have 20. If only 10 of them get 1, meaning that we only open 10 facilities. So when you take the sum of these, it's going to give you 10, meaning that there's going to be 10 open PPB in the region, right? So this will give you the total number of PPBs, and you want to minimize it, but you have a set of constraints that you want to satisfy. You want to make sure that you are covering every single region. So that's your constraints that you have to meet. So for county number 1, you want the number of counties, the number of PPBs that can cover county number 1 should be greater than or equal to 1. There has to be at least one PPB that covers county 1. But county 1 can be covered by its own if you have a PPB at county 1, or if you have at any of its neighbor, 2, 12, 16. And where do we get those? From our list. I'm going to go back here. 2, 12, 16, and 1 itself, 2, 12, 16. If you add these decision variables together, x1 plus x2 plus x12 plus x16, it's going to give you the number of PPBs that are eligible to cover region 1, county 1. So you want this to be at least 1. There has to be at least one county that is eligible to cover county 1, right? So you want to have at least one PPB that covers county 1. And let me just do it for the last one. For Carroll, you want to, the counties that can cover the county number 20 are 20, 11, 14, and 19. So x20 plus x11 plus x14 plus x19, that has to be greater than or equal to 1. And that will make sure that the last county, county number 20, is covered. There's at least one county, that at least one PPB opened that can be that is eligible to cover county number 20. And when we solve it, this is actually the optimal solution. I'm going to go in Excel and we're going to review the answer. We're going to solve it together. But I just wanted to show you this. This is the optimal solution. This is the map, actually. This is the geographical map of 20 counties. And by having three, as you can see here, these 3 stars, 7, 11, and 12, we're going to see how we can find those. But this is one solution. This is one set that can cover the whole thing. Let's see. So 7 can cover itself, 5, 4, 9, 8, 18, 17, and 6. So they're all covered. If you have one PPB here, they're all covered. When you have one at 12, 1 is covered, 16 is covered, 13 is covered. I'm not sure if 10 is covered because it doesn't have, it's just 1 point. I don't think it's eligible. We can go back to our list. Let's say 10. Let's see if 10 is covered by 12. So that is covered. Actually, that is considered to be a neighbor. So 10, 2, 3, 10, 13, 16, 1, 2, and 12 itself. And then if you have a PPB at 11, 19, 20, 14, 15, 13, 10, 8, and 18, and 11 itself, they can all be covered. So as you can see here, by having these 3 PPBs, there's no county that is not covered. Basically, they're now the Ohio Trust Company can operate in any of those counties because they have at least one PPB in their neighborhood, right? So I'm gonna go to Excel real quick here, and we're gonna take a quick look at the data, the parameters, and we're gonna try to solve it. Everything is typed here. The set of parameters that we have for this question is a square matrix, as you can see, a 20 by 20 matrix. And the numbers on this matrix are either 0 or 1. 1 meaning they share a border. They can actually, if you have a PPB, for example, this number means that 1 and 2 are neighbors. And of course, you have the same number at the other side. 2 and 1 are neighbors, right? So these 2 numbers. So this means they are neighbor, right? Adjacent. So if you have one PPB, if you have a PPB at 1, 2 can be covered as well. That one is eligible to cover 2. If you have, if you have a PPB at 1, 1 can be covered, 2 can be covered, 12 can be covered, 16 can be covered, and so on. And 16, and that's it. And so on, right? So this matrix, the matrix of parameter, shows you which cities have actually share a border, which ones are neighbor to each other. And then note that on diagonal here, we always have 1, right? Each county can cover itself. Let's say 9 by 9 here. Always 1, 1, 1, 1, always on diagonal. We always have 1, meaning that each county, if you have a PPB there, it can definitely cover its own county. So now our objective function was to find the number of PPBs used. So we wanted to minimize. So so the decision variables are here, the counties, to be whether we are going to open a PPB, principal place of business, at each location. So 20 counties, 20 decisions to be made, 1 for each one. Now, for the objective function, so this is the list of decision variables, 20. Objective function that we want to minimize was the sum of actually the number of PPBs. So if we take sum of the decision variables, All right, it's going to give us the number of PPBs that are going to be established. And so that's it. And then for the constraints, we wanted to have each county to be covered. So for county number 1, we wanted the sum of counties that can cover county 1, we wanted that to be greater than or equal to 1. That's what we wanted. For each county, the number of PPBs that can cover that county to be at least 1, greater than or equal to 1. So for the first one, we wanted to have, if we multiply these decision variables by these actually coefficients, these parameters that define the axis or neighborhood, actually, we can find the number of, we actually can find the sum of counties that are eligible to cover region 1. So here, counties that are eligible to cover county 1, 2, 12, and 16. So if we take this row, the first row, multiply it by the decision variables, it's going to take the actual, if we take the sum product of these two rows, this one and this one, it's going to give me the actual sum of the decision variables that are eligible to cover region 1. All right. So what I'm going to do, I'm going to do this sum product of first row, the list of eligible counties to cover region 1 times the decision that we have to make in terms of opening them. All right. And I'm going to fix and I'm going to lock these values by adding the dollar signs, because I'm going to drag my formula down. So this is the formula for the first region. So I fixed the decision variables and I took the sum product of the decision variables with the first row. Now, if I drag it down, the decision variables are going to be fixed, but let's say for the last county, if I take the sum product of these values, the decision variables, and these 0, 1 values, by this, what this will give me is going to be X, this one, Stark, plus the decision regarding Stark, plus the next one, plus this one, plus this one, right? So, which is going to be what we were looking for in our formulation, actually, in our model. So, and we wanted these guys, these are left-hand sides of constraints. We want each of them to be greater than or equal to 1. I mean, you can just drag that down also. No, it has to be equal 1. All right. So now all is, I think our spreadsheet model is ready. So we wanted to minimize the, let me go ahead and call the solver. So we want to minimize the number of PPBs to be used by changing the decision variables, by changing decision variables C32 to V32. And let me just delete these. I'm going to define them again. So for the new, and then, so, okay, so minimization of the number of PPBs to be established. And then my decision variables are these 20 binary variables subject to the coverage constraints. I want each region, each county to be covered, meaning that there has to be at least one eligible PPB there. And also, one last thing is that I want my decision variables, all of them, to be defined as binary variables. Solving method, simple XLP. Okay, so let's just quickly review it. Minimization of sum of PPBs to be established by changing, decision variables are the row 32, all the decision variables regarding the each location, regarding each county. And I want each county to be covered. So the number of PPBs that are covering each county should be greater than or equal to 1. And then all these decisions to be 1. So let's go ahead and solve this. So going back here, going back to our sheet, we'll see that all of them are covered, and the minimum number of PPBs that you can use to cover this set is going to be 3. So if you open at these 3 locations, Ashland, Stark, and Goga, I think, you will be able to cover the whole set, right? And as you can see here, all the constraints are satisfied.